Hi, I'm Ben-Yaakov. This presentation is entitled Toroid Inductors for Resonant Converters and also subtitled as The Beauty of Finite Element Analysis-Based Simulation. I'd like to thank Stanislav Tishkin for carrying out the FEM simulation which are presented in this video. Also, I'd like to bring to your attention that there are some relevant videos to this presentation. Here are the links, and they are going to be also printed at the YouTube page of this video. The finite element analysis simulation shown in this presentation were carried out by FEM. I'd like to also thank Dr. David Meeker, the developer of this FEM program, and especially for sharing it for free. Let me start off with the characterization of inductors in power electronics. We have in fact two types of inductors. There is I call it the DC inductor. Typical will be like a buck converter. We have here the inductor, and the current is going to, in the inductor, is going to have a DC level, an average value, and then a ripple on it. On the other hand, we have inductors which are used, say, in resonant converters, in which the current is sinusoidal. It's an AC. It's not necessarily sinusoidal, but it is primarily an AC current with little or any DC component. And there is a big difference between these two in terms of losses and the operational point of the magnetics. In the case of the buck converter, or the DC inductor, I should say, we are operating around a certain magnetic field density within the core, and there is a delta B here as the current or as the ripple is developing. This is actually proportional to the ripple here, the delta H, the magnetic field, and the delta B correspondingly depending on the permeability of the material. On the other hand, in the case of the LLC, we are swinging back and forth through the positive and negative, and the delta B is much larger. So we have here a small delta B in general, depending of course on the value of the ripple, while in the AC inductor for, say, resonant converters, we do have a large swing of the delta B. Now, core losses are a function of delta B, that is function of delta I, while the conduction losses of the wires are first of all dependent on the skin depth, which is causing an RAC larger than the RDC, and then same thing for the proximity effects, a function of delta I, the magnitude of the variation of the current. And then we have the DC losses, which are primarily a function of the average and the resistance, of course, of the wire. Let me clear a little bit the issue of proximity, which I like to explain it in a sort of an intuitive way here. If we have two wires, two conductors, and let's say the current is sort of going in here, then looking at the left side or left conductor here, we see that the current passing through here will generate a magnetic field in this direction. And this field actually will reach also the adjacent wire, and therefore it will invoke eddy current due to the induced EMF, or the voltage. And this eddy current, due to the high conductance of the wire, like the copper, of course, the magnitude of the current could be fairly high. And this current, as we can see it now, will, on this end, will actually be added to the current originally injected into the wire, while here it is subtracted. So as a result, we're going to see that the charge carriers, and electrons in the case of a metal, are sort of pushed into this side, and the same thing, of course, will go to the other wire. So we are going to have a situation in which only part of the wire of the diameter is actually being used, so the equivalent resistance, the so-called RAC, is much larger. Of course, if the diameter of the wire is going to be smaller and smaller, then most of the current will be actually passing throughout the cross-section. And if the currents are in the opposite direction, we're going to see this crowding sort of adjacent one to the other. So this is the eddy current. The skin effect is something very similar, except it's not an interaction between two wires, but rather the interaction of the wire on itself. So if we have a current going in this direction, then we are going to invoke the magnetic field, which in turn will cause eddy current. And now what we can see is that on this end here and here, these currents are being added to the current going this way, and in the middle it's going to be subtracted here and here from this current. So consequently, in this case, we're going to see a crowding of the charge carrier around the rim here, while in the middle the density of the carriers will be much lower. So this delta is the skin depth. Of course, it's not a sharp border, but this is just an equivalent representation of the situation. And an approximate expression for the skin depth is this equation 72 over square root of f in hertz, and the result will be in millimeter. This is depending on the conductivity of the material and some other parameters which I'm not going into in this simple presentation. So these are the proximity and the skin effects. Now, one more point to be addressed is the fact that in the case of a power inductor, we do need a gap, because without a gap, due to the high permeability of material that we are using, like ferrite cores, then very quickly as we pass a current through the inductor, it'll go into saturation, while if we sort of dilute the permeability by adding a gap, and this is explained in the videos that I've linked or referred to, then if we do that, then the equivalent permeability is lower. So therefore, with this same current or magnetic field, we are not going to hit saturation. So this is the rationale for adding a gap to lower actually the permeability, the equivalent permeability of the material, so as not to go into saturation. Now, when it comes to inductors, power inductors, they are here shown the basic three types. The basic types, we have here a E-core, two E-cores actually clamped together with a gap in between. We have an toroid with an air gap, and then we can have the so-called distributed gap or iron powder core, in which the ferromagnetic material is actually mixed with a non-ferromagnetic material so as to dilute it, so to speak, and therefore the gap is sort of distributed throughout the core. In this presentation, I'm going to concentrate on these shapes, the toroidal core. Okay, this is the issue of this presentation. Now, when it comes to core losses, we have in the data sheets of the material, of the ferromagnetic material, we have plots like these, which are based on Steinmetz equation, and these are log-log graphs. These are based on measured data, and unfortunately the data is obtained small signal around zero bias, so it doesn't actually reflect all the operating point that we would expect, but this is actually the best we have at this point. So if I compare now a distributed gap core, MPP material with the permeability of 26, which would be practical for high power inductors, to a ferrite core, and this will be of course with an air gap if we are going to use it as an inductor, power inductor. And I'm going to compare them for 200 kilohertz. These are frequencies. This is the swing of the magnetic flux density. Actually, it's the peak value of a sinusoidal waveform, and I'm using it also for a triangular waveform. And this is the core losses in milliwatt per centimeter cube. Same thing goes here, and the swing in magnetic flux density is millitesla here. And again, this is kilowatt per meter cube, which is the same as milliwatt per centimeter cube. So now going back to the comparison, if we look at the 200 kilohertz, we see here for a 100 millitesla peak disturbance or excitation. We compare it here. We see that in here we have about 150 milliwatt per millimeter. It should be centimeter square, I'm sorry. This should be 150 milliwatt per centimeter cube, while here we're going to have 1500 milliwatt per centimeter cube. So this case, and in this particular point that I'm showing, which will be, say, practical for a high frequency inductor, for a resonant inductor, we see that the MPP will have 10 times more losses than the ferrite. This material is 3695, and this is an MPP. Now I can compare it to another point. Here, let's go to 300 kilohertz, and with a small delta B, only 10 millitesla here, and we find that this is 30 milliwatt per centimeter cube, while here we add for the 10 millitesla and 3 megahertz, this is 10 times larger, we found just about the same core losses. This is again should be centimeter cube. So we see that for high frequency, the ferrite core is much better in terms of core losses than the MPP core with a distributed gap or iron powder type of a core. So this is one consideration we have to take into account. So now I'm going through results of finite element analysis, or simulation I should say, done by the FEM package. Let's start with the skin effect. We have here a wire, 1 millimeter diameter, and we're assuming 1 amp current flowing through it. So dividing the current by the area, we find that the density, the current density, is 1.27 amp per millimeter square. Now, using the equations I've shown earlier, for 10 kilohertz, the skin depth is 0.7, so it's 0.7 on each side, and therefore twice the value is 1.4, and if the diameter is smaller than 1.4, then we're not going to see any appreciable skin effect. And indeed, we don't see it here. And if we match the colors here, this is this color here to this color, it's about the 1.27 that we have calculated here. This is what this simulation is showing. Now I move to 100 kilohertz. Now here the skin depth is 0.23, while this is 1 millimeter across. So we can see here the crowding already. This is the density of the carrier, of the current. And obviously, it's not a sharp boundary. It's something like this. This is the density of the charge carriers. And so we see that to where the rim is much higher, and then it sort of tapers off. And again, here we expect a skin depth of 0.23, which sort of eyeballing it seems to be consistent with what we see. And then if I move to a much higher frequency, we see that the crowding is even larger because the skin effect here is, the skin depth is only 0.07 millimeter, or just at the end. The scale here is different from the scale here. This scale here, the maximum is 2.85 m per millimeter square, and here it's 9.5. So it's not the same colors here. The scale of the color is not the same in the two cases. So this is now the skin effect, and now moving to the proximity effect situation and different type of cores. So we are examining here three types of inductors. All of them are around toroids. These are ferrites, and we have a gap here. And the difference between these is that the distribution of the wire, here they are sort of spaced, here they are crowded, and here we have two layers. This, however, actually it's two types of simulation. One with a lower permeability. This permeability is high, it's like a ferrite, and this is like representing a distributed gap core, a iron powder core with a much lower mu, and we'll talk about it in a minute. And also we have done a simulation of an air core, that is the relative permeability equal to 1. Let me just point out that this simulation, or this analysis, this finite element analysis, is two-dimensional. So strictly speaking, it'll be pretty accurate for the case in which we have the lines going all the way. That is, this straight lines here of the windings are long, and we are sort of looking here at the cross section here. Here it is. This is the cross section, and this core sort of goes both way, up and down, and we are looking at this cross section, and so that the edge effect here and here is farther away and not affecting. Obviously, this is not exactly a shape of a sort of a common core, although there are some cores like this, that especially if you stack together a number of toroids. But just for the sake of understanding the phenomena that we are talking about, I think this is okay. So let's first look at the case of a air core. This is an air core, which is sort of shaped a little bit like the toroid, but there is no core, that is, everything is air. And what we see here for 100 kilohertz, we see the crowding of the charge carrier. This, of course, is the case of the current going in, and here it will be current coming out, because this is like a turn here. Okay, it's a long turn. Okay, that is it. So it's going here and back. So I'm looking at these two, and we see here indeed that you have this crowding very close to the one to the other, as I've shown earlier for the proximity effect. So here we see primarily the proximity effect. 100 kilohertz, we should have seen the skin effect as I've shown earlier, but the proximity effect is much more important here. So we see very nicely this effect here all over the wires. Now this is the same 100 kilohertz, except that the scale here is different. Again, although the color is not that strong, I mean, it doesn't go into the red, but again, the scale here is 9.5, and here it is again 2.8, so it's different scales here. And here we see the magnetic field, which is built between the wires carrying the current. Very nicely, you see them in between. And this is finally for 1 megahertz. Of course, we see the same thing, except the crowding here is much stronger, because the effect is a function of the frequency. Now we move to the ferrite core with a gap. This is a ferrite which is assumed to have a relative permeability of 3000. This is very typical of ferrite cores. And if we look at the color here, we see the concentration of the magnetic field within the gap. This is consistent with what we would expect, and again, this is covered in the videos that I've mentioned earlier. And if I sort of try to compare the colors here, I see that this is around, say, 10 to the 4 amp per meter. Okay, that's 10 to the 4th, 3. This is about the color here. Okay, so let's do some calculation to see if we can come up with this number, or whether this number here, what we find, is consistent with the actual analytical calculation. So we have a case here in which we have a ferrite core. The radius is 4.5 millimeter, the gap is 0.3 millimeters, the magnetic path length is 28 millimeters, and again we can say, and this is again from the theory, that the relative permeability, the equivalent relative permeability of this body, of this structure, is the length here over the gap length, which comes to be about 100. Okay, so this is the permeability. Now, this means that the field here is much stronger than the field around within the ferrite. Again, you can look at it this way. The flux should be, magnetic flux density should be about the same, and since the permeability of the ferrite is much higher than air, it's 3,000 higher, then when you divide B by the relative permeability, you get a number which is much smaller than in the air. So therefore, we could say that all the magnetic field is concentrated here. Now the length is 0.3, and we have 10 turns of 1 amp, so the magnitude of this magnetic field is Ni over Lg, and for the numerical values that we have here, this is 10 turns times amp, and this is the 0.3 millimeter in meters, and we find that according to this calculation, the magnetic field strength should be 3.3 to the 4th, very close to what we find here. So everything seems to be falling in place and consistent. Now we see here the magnetic flux density B, again for the same case, and it should have been like a constant B, because the magnetic flux is supposed to be the same lines here. However, there are some fringing here, so it's sort of diluting a little bit the density of the magnetic flux, and therefore the field here, magnetic flux density within the gap, is lower than here due to this spreading of the lines here. Okay, so this is why we see it at a lower intensity than within the ferrite. And now the current density. This is 10 kilohertz, so there's no skin effect here actually. It shouldn't affect it, but we do see already some proximity effect, and this is due to the magnetic field around the gap. As we have seen, there's a very strong magnetic field here, and it's affecting the close by wire. So this is for 10 kilohertz. 100 kilohertz, we start to see more of a effect of one wire on the other. Okay, we see it here, and of course, if I move to 1 megahertz, then the intensity of this effect becomes much larger. We see the effect again of this gap very strong on these two lines which are close by, and then we have the effect here of these. Notice that these are less affected than these, because we have an opposite effect of the right wires on here and the left wires on here. They are sort of canceling each other, so therefore it's less of a field, but still there is quite a bit of crowding, as we can see it here. This is again 1 megahertz with a different color scale. And then we move to the case of the crowded wire, that is the wires which are wound one by the close one to the other. And again, we see this is 1 kilohertz. We see here the edge effect is primarily due to the wires rather than the gap here. Okay, so the current here is affecting this edge effect, and the current here, this wire which is at the end here, and there's quite a bit of crowding here, as you can see. We'll summarize everything at the end. And this is another shot of the 100 kilohertz, different color scale. And here we see the 100 kilohertz in a close-up, zoomed picture, which is kind of very, very nice. We see here the crowding of the current at the edges. We see the magnetic flux here. We see some strange phenomena here due to the interaction of the magnetic field and the current within the inductors. It's a beautiful picture, and as I've said, we see that these lines or these wires are less prone to effect of the magnetic field because these two are sort of canceling each other. Very nice picture here. And this is 1 megahertz. Everything is the same except the intensity is much, much higher, as we can see it here. And again, 1 megahertz with another color scale. Now I move to the 2-layer, and here we can see already that the second layer, this is actually very known, and it shows up in the so-called dual equation, that the magnetic field here is much higher than here, so therefore the crowding and the proximity effects is much more noticed in this upper layer. And finally, I go to the distributed gap with the mu 100, which is the same as the relative permeability of the ferrite, the total structure, as we have calculated earlier. So it's the same in terms of the, like, it will be the same inductance for this inductor, for this core, or for this case, and the ferrite case, so with the air gap. The inductance obtained with this winding will be the same because the permeability is the same, and the dimensions are, of course, are the same. So at 100 kilohertz, we see a moderate effect. And what is really happening here is, first of all, we don't have the sharp gap and the very high magnetic field, and also the ferrite material, although it's a lower mu, has the effect of actually arresting the magnetic lines here, which are sort of finding their way into the material with the lower reluctance, and this is why we don't see the proximity effect as strong as we have seen it before. Now, comparing then the 3 or more than 3, all the cases, we see here the spaced winding, the crowded winding, the 2 layers, and this is the ferrite, and this is now the air core. Obviously, the inductance of this structure will be much lower than here because the mu is much lower. In fact, it will be around 100 times lower. So therefore, to get the same inductance, you will have in the air core to add many more turns, and obviously the total loss will be much higher, although there is no core losses, but you need much more wire in order to obtain the same inductance as in these cases. And here is a comparison of the actual resistive losses of these structures, and this is obtained by the FEM package for the different wires. So they are labeled here, and we can already see from just looking at the colors here, this is for 1 megahertz, from the colors here, that This is the best case. We see here numbers in 10 to the minus fifth. This is for a depth of 1 millimeter. It's like a cross-section of a diameter of 1 millimeter and a depth of 1 millimeter. And we see here to minus 5. This is probably the worst. It's minus 4. And this is also not that good. This is sort of in between. We have here lower numbers than here, of course, and here, and we can just from the color get the same impression here. So the conclusion here is that, in fact, in terms of proximity effect, the distributed gap is the best. But core losses will be very high if you use it for resonant converters. However, for the case of regular PWM converters, in which the delta I, that is the ripple current, and therefore the delta B expected in the core is small, the iron powder core will have advantage because the losses due to the skin effect and in fact the proximity effect will be much lower, considering the fact that the magnitude of the AC component of the current is much smaller. So in these cases, a distributed gap core will be better unless you go to very, very high frequencies, and then of course even a small delta B may cause large losses. Now also, of course, I'm showing here a large diameter in order to sort of emphasize the effects of both the skin and proximity effect. In order to reduce the losses, you'll have to use a diameter which is much, much smaller. That is, the skin effect or the skin depth is perhaps an underestimation of how small should be the diameter. In fact, the diameter should be much smaller than twice the skin depth because of the proximity, that effect that we have in here. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.